problem worksheets, everything, and they'll even give you can even input, if you're graphing, you can even input the Z code.
Do 3D graphing?
Yeah.
That's cool. Interesting. 3D graphs are one of those things where everybody goes, wow, that looks really cool. I have no idea what's going on.
Yeah.
Sure looks pretty, though. Okay, for today, we're not going to do any graphing. Definitely not in 3 dimensions. So we're going to just continue on, and I know we're skipping a little bit ahead. We will be kind of settling down on some chapters, but we're going ahead to Chapter 4, Section 2. 4.2 is defining the trigonometric functions, and I've never really been happy with the way that they just kind of dive into calling things sine, cosine, tangent. Let's just call this a sine, cosine, tangent, and hope that everybody at least memorizes these and understands what's going on. And yeah, you do have to understand what's going on, but I think we can approach it in a slightly different way. So that's what we're going to go ahead and give it a shot here today.
I hate this section.
Well, you'll love it after this.
I hope so.
Serious?
I hope so, too.
Try on it.
Okay, well, we have a right triangle, and let's go ahead and give some dimensions to this, the way I've drawn it fairly proportionately. I think everybody's familiar enough with a 3, 4, 5 right triangle that it lends itself really well to giving a definition of what things are happening here, because fortunately they're all whole numbers too. So 3, 4, 5. Those could be anything: inches, meters, feet, miles, whatever. But 3, 4, 5 triangles, they're really nice to define things with because they use 3 whole numbers. Now you know from having used Pythagorean's theorem that sometimes you might have whole numbers for these two sides, but then you calculate that square root and it doesn't always come out a nice even number. Sometimes it's going to be, 3, 3, and then some crazy long number that you just finally have to abbreviate some decimal places. But the 3, 4, 5 is nice because they're all whole numbers. Now this 3, 4, 5 triangle, no, not quite. I'm trying to draw this to scale as I can. Okay, can you tell me anything that you might know about that already?
Double the size of the first one.
Well, C is a 90, the hypotenuse is 10. Yeah.
Come
They're called with similar triangles.
Take a break here while our equipment returns to us. Okay, good. We're back. Okay, so we can look at these two triangles, and what do you know about these two sides being scale of each other? What do we know about this third side?
It's 10.
It's going to be 10. How did you determine that?
Because 4 times 2 is 8, and 3 times 2 is 6.
So we doubled both of these to get these, and knowing that similar triangles mean that we can just double this, and we know that we've built an accurate triangle. So assuming that these are 90 degrees, that's something that from now on, I'm probably not going to draw that every time. We'll just assume that now we're doing right triangle geometry. It's a right triangle. So it's a 90 degree. Obviously, if we started changing this, then all bets are off and it's no fun anymore. But for now, we're going to stick with this 90 degree idea. And so if we double the size of this and this, we also double the size of this. That's what we call a ratio. So the ratio, when we've increased a number, if we can tell how much we've increased it by, and in this case 2 times, each one of these is going to be 2 times the size of the other one. Now if this was a 90, looking at the size of these, would we agree that these also have to be the same?
Yes.
For that ratio to hold true? Because if we just increased this one and doubled it, but we tripled this one, that angle has now changed. So as long as we're doing the same thing to every one of the sides, and in this case doubling it, we know that it's a scale model, it's just scaled up, and we also know that this angle is the same. So angles, we'll be using this symbol a lot. This is called a theta, a Greek letter theta, which is used all the time for angles. So we can say in this case, those two angles must be the same. They can't be different if we have a 3, 4, 5 going to an 8, 6, 10. So if we made ratios of these sides, and we could pick any two sides that we wanted. Let's say this side, we'll call this A, B, C, A, B, C, just to keep it consistent. So A, B, and C. If we took this and said, let's make a ratio of A over C, just to see how those two numbers relate to each other. So A over C would equal, what happens when we put in the numbers there? What would we get? What's A? 4. And C? C is 5. Like I said, we could pick any one. This is just, let's just pick A and C. And let's see what happens. Now let's do it over here as well. A over C, what's A? 8. And C is 10. What happens when we reduce that? What's 8 tenths? 4 over 5. The thing that was consistent about this is the angle. So theta equals theta. For the two triangles, we scaled them up, but the angle is the same. So that means that if we are given that angle, whatever angle that happens to be, and we'll be dealing with angles throughout the rest of the quarter, but if that angle is the same, no matter how much bigger we make this triangle, that ratio of A over C is going to always stay the same. It's going to get, the numbers are going to get bigger and bigger and bigger, but if we finally simplify them down and reduce them down to as low as we can get, it's 4/5. And what is 4/5 as a decimal number? Can you plug it into your calculator? 0.8. So that means we could say, well, this ratio, we could call it 4/5, or we could call it 0.8. And the reason I'll use both is some calculators by default will give you fractions. Some calculators by default will give you decimals. Either one is just fine. 4/5 is the same as 0.8. Doesn't matter which one we're dealing with, but we can work with both of them just to always show that we can work in either one we want. But that ratio between those sides is going to be the same. So does that statement also hold true if we use A over B or B over C?
Yeah.
So let's try B over C. Just we'll kind of go through that one quickly. B over C equals 3/5. And what is 3/5?
It'll be 0.6.
0.6. Okay, so did the same thing. Just pulled in the numbers from this triangle, simplified them down. We can verify that sure enough, we doubled the size of the triangle, but that ratio of those sides stayed the same. No matter what size we increase this triangle to, if we keep the angle the same, that ratio is going to stay exactly the same. So what they did is they just came up with pretty much all the combinations we can get of different ratios of, let's do B over C, or A over C, or A over B, or B over A, or there's 6 of them total. So there's 6 possible combinations that we can make out of this that are unique using 2 sides. So what they've done with that is they took all 6 of those combinations and gave them names. Just said, we're going to put this into a function that a calculator can use, but it's going to be the definition of when we have this angle in a right triangle, we know that this ratio between these sides is always going to be the same for that angle, no matter how big or small that triangle gets. So from that, we arrive at this list of names. And this list of names starts with sine. And sine, they always put that angle after it because they're saying the sine is a ratio, but it's going to be unique for every angle. That was the constraint we had to have to say that those two triangles were similar. We couldn't just say, let's just change the angle and hope that they're the same. No, they won't be the same. If we were to change that angle in between, that ratio would have been different between the two triangles. So as long as we keep the same angle, the sine is going to be a ratio that, if we're using our notation over here, A, B, and C, and we'll kind of switch in a second to a little bit more consistent one, because A and B are kind of arbitrary. We could flop A and B around. But looking at this triangle and this angle here, is the ratio of B over C. So yes, there is some familiarity we have to do, and I'll give you some mnemonics that make these a lot easier to remember. One of the ones that I always use, and I still use every time I look at these and go, how do I remember which ratio it is? But that's really all that we're doing here is saying, for this angle, whatever angle of triangle we've drawn here, there's going to be a ratio that defines B in relation to C. So B is going to be some size, C is going to be some size, and they're going to have a set ratio no matter how big that triangle gets. If we change the angle, it's going to be a new ratio. And then cosine of theta, A over C, and these first three, sine, cosine, tangent, are the most familiar ones. So we'll hit the other three, but kind of breeze through those, enough to at least define those. But sine, cosine, and tangent are the really handy ones. Those are the familiar ones, so those are the ones that we'll be sticking with for the most part. But tangent, now, I would not suggest committing this list to memory. This only works for the triangle that we've drawn here. Like I said, we'll be switching over to a more consistent set, and traditionally using X and Y. When we're graphing things, we've got Y-axis and X-axis, and those don't change. So that's why it's a lot easier to memorize, or a lot more familiar to memorize these with X's and Y's in them, and R's, that's another thing, a radius, because those are not going to change arbitrarily based on, well, what if we called this one B and this one A? Then we'd have to change these. So don't commit this one to memory. This is just a nice one to relate it to this triangle. So sine is B over C, and I'll give you that mnemonic. And I originally learned it, a pre-calculus teacher. We were going through this whole thing, and he basically said, if you can remember this name, SOHCAHTOA, and every time I use this, I still think of this word, SOHCAHTOA. You know, some Indian princess or something. I don't know, whatever you want to relate that to. But if you can remember the name SOHCAHTOA, there's a handy way. It's actually, in every single one of these, it gives you a relation between the two. So group it into three. That's SO, S-O-H. Sine equals opposite over hypotenuse. That's going to be the format for all of them. Sine equals opposite over hypotenuse. So, SOHCAHTOA. Sine is equal to opposite over hypotenuse. Now let's kind of stop there for a second before going into the others and see how does that relate to B over C. Sine of an angle. Where is our angle? Kind of obvious. We're looking at the one on the far right side, left side, far left side. That's the angle that we're looking at. Which side of this triangle is opposite, which means the furthest side that we can get from it? A, B, or C?
B.
B. Just like when we were using the lowercase versus capital, we always said the opposite sides matched. So the angle that was uppercase matched the opposite side, which was the lowercase letter. So we basically draw a line as far away as we can get, whichever side isn't touching the angle. It's another way to think about it. Of all these triangles, or of all these lines in the triangle, lowercase b is the only one that's not touching that theta. It's the only one that's not in contact with it. So that means it's our opposite side. Hypotenuse is the only diagonal one. So hypotenuse is always easy to remember because it's C. So that means the opposite side is B over the hypotenuse C, B over C. So if we can remember SOHCAHTOA, we can look at a triangle and say, well, where's our theta? What angle are we asking about? And if that's our angle, we can say SOHCAHTOA, sine is opposite over hypotenuse 3 over 5. So does that kind of make sense, at least as far as the mnemonic goes? Probably just repeat that all the time, SOHCAHTOA. And go on to the next one. CAH, cosine equals A and H. Well, the H, we've already used that. That one's familiar. A is a side, which means adjacent. What does the word adjacent mean? Adjacent to something.
Next to.
Next to, beside, touching. Of these two lines, the horizontal or the vertical, which one's touching the angle? A or B?
A.
A is the only one that's touching the line. Hypotenuse is still hypotenuse. We're not going to mess with hypotenuse. So our adjacent is A. The letters happen to match, but don't be fooled. I just picked A, B, and C. That was kind of random. But adjacent is the line that's touching the angle that we're dealing with. So adjacent, in this case, is A. Hypotenuse is C. Cosine equals A over C. That's what we've built up here. And then finally, TOA, tangent. Somebody want to give that one a guess? Using O and A?
Opposite over adjacent.
Opposite over adjacent. Opposite over adjacent. So, looking at this angle, which one is our opposite side? Which one is not touching the angle?
B.
B. Which one is adjacent?
A.
A. B over A. And right before I wrote those down, I was like, SOHCAHTOA, sine is opposite. Okay, that one's a B over C, A over C. So, no, I don't have all of these. Like, I can't just look at a triangle and be like, oh yeah, I know everything about this. Like, okay, SOHCAHTOA, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, that means tangent is opposite over adjacent. So that mnemonic has really helped me out a lot. So you may know some others. I'm sure that with every mnemonic in math, there's always good ones, bad ones, funny ones, inappropriate ones. It always happens. So I'm sure that there's others out there. That's not the only one, but it's one that helped me. So if you find another one, then feel free to use that. But it really helps this process of clarifying which is which, because the ratios are really hard to just memorize. It's really hard to just commit to memory which one is which. So at the very beginning, you just write this word down. That allows you to derive every single one of them just by mnemonic. That way you don't have to commit 6 things. Sine is X and Y's and R's, and you don't have to memorize those. You just write down adjacent over opposite. That way, even if they throw you a curveball like, hey, we're not dealing with this angle anymore, they're asking you about this angle. Well, at first, oh, that's a curveball. But if we can remember sine is opposite over hypotenuse, what's opposite to this side?
A.
A. So our sine of that angle is going to be sine is opposite side over hypotenuse, A over C. So if they throw us a curveball and say, we're not looking at this angle, we're looking at this one over here, you just remember SOHCAHTOA. Sine is opposite over hypotenuse. What's the opposite side? What's the hypotenuse? So that means that if you plug those numbers into a calculator, and we say sine, and you take your calculator and push the sine button, it's going to ask you for an angle. We can give it any angle of some right triangle, 0 to 90 degrees, and if we hit equals, it's just going to give us some decimal number. It's going to give us a point something between 0 and 1. So what that's really doing, and well, it can give you negative numbers too, but we'll define a lot more of these regions as we go through it, because every single one of them makes perfect sense. But if sine, let me go ahead and clear some of these up. In fact, has everybody got this part? Let me erase this so I got a little bit more space here. And if there are any questions about it, just stop me and let me know. There, generic triangle. Actually, let me erase the whole thing. Rebuild it again. Mostly because I accidentally adjusted that, and so everything's leaning off a little bit to the side. Technology is really handy, but it's kind of getting in the way sometimes too. So let's take this triangle again. And we'll keep it the same one. We're going to call this theta. So that's going to stay the same. But now we're going to move into that world that has a little bit more of that absolute instead of just an arbitrary, let's choose whatever we want to call A or B. That C was always staying the same, and we're going to use a letter R for that, a radius. And I'll show you how that radius works in a little while. Basically, it means if we took an X and a Y, which forms that XY grid, that square, and we had a certain radius out from the very center of it, we could trace that radius all the way around and make a circle. And here, all we've got is from here to here is just a point on that circle. And then coming down through the middle, draw that cross shape. That's our XY coordinates. And that radius means if we were to draw a circle, let's just stop somewhere along the way, see where we are, and it's going to have formed an angle with the x-axis. That's really the whole idea with using these absolute numbers is x and y. And you remember from graphing, stays the same. X is the horizontal, y is the vertical. So we're not going to mess with that, which is actually really handy because the more we can keep things consistent, we just then build on things rather than having to change our perspective around. And so keeping x and y as what we remember familiarly as x and y, then we can just keep this whole thing the same. But that means that with this triangle, here to here is along which axis?
X.
Here to here is which axis?
1.
It's the height, which follows along this one, x and y. Those are our two axes. Now, with the knowledge that x and y, even though the angle might change, x-axis is the horizontal. The y-axis is the vertical. The angle in question is that angle that it makes with the x-axis. Therefore, we can now start redefining sine, cosine. These are the ones that we want to get a little bit more familiarity with. These are going to be the absolute definitions using x, y, and r. They're the ones that aren't going to change. So if we do that, go ahead and rebuild them. Remember SOHCAHTOA. Sine is opposite over hypotenuse. Which one is the opposite side now to this angle?
Y over R.
So the opposite side is
Y.
y, the only one that's not touching the angle. R is touching it, x is touching it, y is the only one that's not. So sine is y, and the hypotenuse, always r. That one's handy. Because the diagonal line is that radius. And cosine then, x over r, basically the other straight line over the hypotenuse. Now the tangent, the TOA, SOHCAHTOA, which one is the opposite side now? Which one is opposite?
Y.
Y, and then the adjacent is x. Y over x. So we've now built 3 out of those 6 trig functions, and we will go over the other ones, but like I said, we'll do that enough to at least then we know what we're talking about when we say sine, cosine, tangent, and then secant, cosecant, and those other interesting ones that are certainly useful. They're certainly a valuable thing to know, but not used quite as often as these. So that's why we'll spend a little bit of time on them, enough to at least be able to speak the language, but then move on and focus on these mostly for the rest of the time. So sine, cosine, tangent. And there's a reason that I wrote them in that way. And here, for some reason, I don't know why, but for some reason they've decided to throw us a little bit of a curve when whoever was first coming up with trig functions decided to come up with the names for these. If we had sine, cosine, tangent, we would imagine that if we did something to those and made something that related to sine, cosine, tangent, we would match this one with secant, cosecant, and cotangent. Because those names, at least they follow the same pattern. There's the sine and then the co of it. There's the secant and then the co of it. But they decided that they weren't going to do that. So, even though this looks like a little bit of a mistake, it's not. Cosecant goes with sine, secant goes with cosine. But fortunately, that's the hardest part that we have to remember. That and SOHCAHTOA. So if you can remember SOHCAHTOA, and then after that you can remember that, okay, the cosecant and secant, I just need to remember to flip those around. So cosecant goes with sine, secant goes with cosine, but check this out. We had y over r. I'm just going to flip it over. So if you can remember SOHCAHTOA, you can remember the first three. I guarantee you can get the other three, so you just flip them over. So what do you think secant's going to be?
X over, or
R over
R over x. What do you think cotangent's going to be?
X over Y.
X over y. And we're done defining all 6 of them. So 2 things to keep in mind. SOHCAHTOA, the mnemonic for remembering the first 3. And then after that, remember that cosecant and secant are inverted of what you'd think they should be. Cosecant goes with sine, secant goes with cosine. Even though it seems backwards, if you can remember that, I guarantee you can put these ones together. Just flip them over. They're the inverses, and a fractional inverse in math just means take that fraction, flip it over. That's an inverse. So we've just inverted those, and there we have it. We've now built all 6 of those trig definitions. So in the homework set, they're going to give you some triangles or pieces of triangles, and they're going to say, build me all 6 of those. Put all 6 of them together and tell me what the trig functions are. So let's go to problem number 4, exercises 4-2, problem number 4. Go ahead and put this here. So it says, find the values of the trigonometric functions, that's all 6 of them, for a line that passes through a given point. Now, ordered pairs. Remember for points from graphing, if we had a set of parentheses with the comma in it, which is which?
X and Y.
X comma Y. Okay, so we got that. They've given us a bunch of ordered pairs. So could we stick this point on our circle here?
Yes.
What is X for problem 4?
5.
5. And what is Y?
12.
12. So we're probably looking somewhere right about up here,
Yeah.
right? So I'm just kind of making a reasonable estimate of if this is 5 and this is, oops. My brain today. 12. Still the right triangle?
Yep.
Yep, still got a 90-degree angle. So 5 and 12, what more do we need to finish the rest of the trig function, or to build all the trig functions?
R, which you can use Pythagoras theorem.
Which we can use Pythagorean's theorem to find the other one. So as long as we have an ordered pair, it's really not too hard to find the r value, the radius. And what would we do to find that?
5 squared plus 12 squared.
And then take the square root. So as a formula, before we were using Pythagorean's theorem, which was c squared equals a squared plus b squared. Well, let's turn that into r, x, and y, just so that it stays familiar. R squared equals x squared plus y squared. That way we know exactly what numbers to pull in. And what does r end up being? Once we square the other two, we add them, then take the square root. R equals
13.
Okay, and fortunately through this list, they've given us mostly pretty convenient ones. They actually come out with whole numbers, which is pretty handy. But if it wasn't whole numbers, that's okay. We'd still get a number out that we could plug into these ratios. Yeah, it seems like, well, this isn't a really easy number to work with. It's not a whole number, it's a decimal number. Oh well, you can just put it onto the bottom of a fraction, or onto the top of a fraction. It doesn't matter. Really? So,
Just on.
Okay, so let's start building these. The more you get through these, the faster it's going to become, the more familiar you're going to get with them. So, sine, what's SOHCAHTOA? Sine is, I know I just erased them, but this is kind of intentional.
Opposite over adjacent.
Opposite over hypotenuse.
Yeah.
Opposite over hypotenuse, and that's, which one is the opposite side of the angle? 12
over 13.
12 over 13. Okay, that problem's done. What about cosine? Adjacent, which is
Over
13.
5 over 13. Tangent is TOA, SOHCAHTOA, opposite over 12 over 5. Yep, because opposite over adjacent.
Yeah.
And now that we've got the other ones,
Flip them. Yeah, flip them.
13 over 12, 13 over 5, 5 over 12. Whole thing is done, all 6 of them. Remember SOHCAHTOA, and then remember these ones are backwards what you think they should be, and it actually gives the full list here on page 113. It gives all 6 of them, and it lines them up the same way, but I always like to emphasize, they usually just gloss over it and go, cosine goes with sine, but when you're trying to memorize those, it seems backwards. But as long as you know that it is backwards of what it's supposed to be, then it kind of puts that trigger in your mind that when you're writing them out, oh yeah, it's supposed to be backwards, intentionally, for whatever reason of whoever was first coming up with all these things. They decided it was supposed to be backwards. But maybe they didn't speak English. Maybe it was before then, so maybe it's just a poor translation or something. So we really don't know who to blame. So now that kind of leads to another point of, if we know the sine value, can we find the others based on that? Do you think we can? Let's see if we can. So, this 12, well, even cosine equals 12 over 13. Okay, so let's do that one. That one's problem, problem 18, because it's an even numbered one. The odd numbered ones you can look up in the back of the book. Okay. So what does 18 say?
18.
Sine equals 1 over 2.
So sine equals 1 over 2. Find the others.
Find cosine.
Tangent. It really doesn't seem to not really give us that much information. Like, where do we go with that? What does that really help us with? 1 over 2. And that's all we've got. But what does that tell us?
That gives you 2 sides to Pythagoras. So
It gives us 2 sides of a right triangle. So not only that, but we can also start with kind of drawing a sketch of this. It won't be perfect, especially not for artistic skills here, but we can at least draw a little bit of a representation of what that circle is going to look like to give it some more physical perspective. I'm sorry, what that triangle is going to look like, not circle. Okay, so it says 1 over 2. That means that sine is which one, y or x?
Y.
Y. So that means the height, the vertical distance, is exactly half of the radius distance. Yeah, it's kind of hard to know exactly what that's going to look like, but we can at least give it a little bit of an estimate and say it's probably down here somewhere, because that line that I've drawn seems to be about half the length of that one. The ratio is 1 to 2, which means that for every 1 that it goes up, the radius goes out 2.
Yeah.
So
Rise over
this
rise.
is 1 and 2, because we knew that sine is y over r. So they basically told us with that, what's y and what's r? Well, y was 1, r was 2. I'd call this problem pretty close to being done now. I mean, there's a few more steps. Can we figure out the third side from that? X?
Pythagorean theorem.
Yep. So solve for one of them. So that means x is going to be equal to the square root of r squared minus y squared. I know I took some leaps and bounds there to get that, but does that make sense?
Yeah.
We just took r squared equals x squared plus y squared, rearranged it, and then stuck a square root over the top of it. What do we get for x? Like I said, it's not always going to be a really nice, even number. 1.73-ish.
Yeah.
So let's go ahead and plug these in and see if we can at least keep it a whole number. So x equals, and what's r? What is the radius? 2. They gave it to us here. So the radius is 2. We square that, we get 4. We take away 1 squared, which is 1. So
1.73.
square root of 3. And we could either keep it there, and sometimes I kind of like keeping it here because otherwise you're like, yeah, this is a huge decimal number. We could cut it off somewhere, or we could just leave it as root 3. And it's kind of whichever is up to you. If it was on a test and I gave you a problem like this, I'd accept either one just fine. But sometimes the book will say, please leave this as a rational number or something like that. And then it's usually better to just leave it as a square root of 3. That way you know you're getting an absolutely perfect answer. You didn't round anywhere. But then the square root of 3 never really helped anybody in real life, whereas 1.7 feet was probably a lot easier to measure than just cut me a board that's a square root of 3 feet. No thanks. So it's kind of that bridge of, well, the math book is going to ask for this, but in real life they're probably going to just want you to give it an estimate. So I don't care which one you use. So if x equals the square root of 3, and we'll just keep it there just because that's probably what it's going to look like. Probably in the back of the book it'll keep square roots in it. But now, can we finish filling in all those? I think it only asked for find, in that one it's 18, find cosine of theta and cosecant of theta. Well, let's go ahead and find all of them. Just because we're already here, we might as well just get a little bit more practice in. We've already determined they're not that hard. So cosine is, which one?
Square root of 3 over 2.
Square root of 3, because that's the x value, over 2. What about tangent?
1 over square root of 3.
And then let's just flip them. Okay, all 6 of them. Now sometimes if we do run into things like this where you look in the back of the book and the square root thing is up on top, I'll explain that, but you probably got the right answer. What they do is they call this thing called rationalizing the denominator of a fraction. They say, hey, if you got a square root in the bottom of your fraction, then that's not good. For some reason, they don't seem to like that. And that's one thing that's always kind of confounded me because I'm not entirely sure why you can't do that. But in my experience, you just make it a number anyway. So I just plug it into the calculator and see what decimal approximation. But there's this method that they call rationalizing the denominator. And that says if you have a square root in the bottom of the fraction, please don't keep it there. Do something with it. Like in this case, 1 over square root of 3. It says that's not good. We don't want a square root in the bottom of the fraction. So how do you turn a square root into a number? What do you do to undo a square root?
By itself.
You square it, or you just, multiply it by itself. So if we took this and said, multiply by square root of 3, and did the same thing to the top, think of it this way. If you take 1, and or if you multiply something by 2 over 2, what's 2 over 2? 1. So you basically just multiplied by 1. Didn't change anything. If you do the same thing, root 3 over root 3, what's square root of 3 divided by square root of 3? What do you get? 1. So if we do something on the top and the bottom, we're just multiplying by 1. We changed the way it looked, but we didn't change the value of it. So this is the idea that they call rationalizing the denominator. So we're going to get, what's the top going to be? What's 1 times square root of 3?
Square root of 3 over 1.
Not over 1.
Or 3, I mean.
Square root of 3 times square root of 3, it basically undoes that little square root symbol, or just erase the square root symbol and you're left with a 3. So that means, even though they look completely different, those are the same thing. They called it rationalizing the denominator because it's a better practice to not put an irrational number in the denominator of a fraction. Again, one of those kind of things where they seem to emphasize it a lot, but in real life, you're probably going to make that a decimal number anyway, so I'm not too worried about it. But if you see that in the back of the book, and your answer does not seem to match, what you got is not what they have in the back of the book, you may not be wrong. It may just be that they've taken it a step further and rationalized the denominator. So if you can just do this, multiply by whatever that square root is on the top and the bottom, and just see what you get with that, and it'll probably match that answer. So hopefully that's not too confusing there with that extra step in it. I'm not going to require that. If you do the homework, I'm not going to require you to have rationalized the denominator on it, but just be aware that if you're checking your answers and it comes up with something different, that may be the reason for it, and you may both be right. So given a function, finding others, and then finding the values of the trig functions, and that's pretty much the extent of what that section has in it. And we have a couple of minutes left, so are there any questions about it?
Homework.
Homework? What's the homework for it? Well, that's a great question.
Oh,
Yeah, 3 through 28, all of them. So the even ones are in the back of the book. The odd ones are, odd ones are in the back of the book. Even ones, I can certainly go over in class. Let's see.
Email to us?
What?
Just email us the evens.
Just email the answers. Sure. Let's take a look at 25. It's just a little bit, the assignment is just a little bit vague for that one. So let me go over the description of that one just so you know what they're asking for. And basically saying, we looked at a point where it said, here's a point on a graph, x and y, and now tell me what the trig functions are. This one's just saying, well, prove to me that the trig functions are the same for all three of those points. So they'll give a set of points. Now the first one, what is the first one? What kind of triangle? Or problem 25. What kind of triangle is that? Look at the two numbers.
Right. 3, 4, 5.
It's a 3, 4, 5 triangle. Because x is 3, y is 4, the r must be 5. 3, 4, 5 triangles. What's that next set of parentheses?
6, 8, 10.
It's a 6, 8, 10 triangle. That was actually the very first one that we put up on here. So now we look at, hey, would 4.5 and 6 both be on that line as well? 4.5 and 6. Let's see what happens there. Prove it kind of by a reasoning approach, but then also by plugging it in and seeing if that works. So by the reasoning approach, if we take a 3, 4, 5 triangle, so 3, 4, 5, actually that one was, yeah, so x is 3, y is 4. So that's a 3, 4, 5. What we're saying is, could we increase the x and the y to make it 4.5 and 6 and still get the same ratio? 4.5, 6. We don't know what the other one is, but what did we have to do to 3 to get 4.5? What scale did we have to increase it by?
1.5.
Is 4 1.5 times bigger than 3?
No.
Want an easy way to find out? So if you can say, let's take 3 and multiply it by some number to get 4.5, we can go backwards, just backdoor it. 4.5 divided by 3 gives us that number that we had to get, that we had to multiply by to get there. And what is that number?
1.5.
1.5. That means that we took 3, made it 1.5 times bigger, and got 4.5. Well, reasoning says if it's the same triangle, we should be able to do the same thing here. Take 4 and multiply it by 1.5. What do we get?
6.
6. So by that logic, what would this side be?
7.5.
7.5? Again, lots of ways to check that. Pythagorean's theorem. We could check the sine and cosines and make sure that they all come out the same. So sine and cosine, let's do it just for the heck of it. Because more practice is never a bad thing. And because we have extra time. So for the original one, the 3, 4, 5 triangle, what was the sine value? sine equals y over r, which is y over r,
4 over 5.
4 over 5. Good. And what is 4 over 5? When you hit it, you put it into your calculator and hit equals 4 over 5? 0.8. So 0.8. Let's do the same thing for this triangle. Instead of 4 over 5, what do we get now? Y over r. Y is the height, which is
6 over 7.
6 over 7.5. Good. What does that equal when you type it into your calculator? 4/5, which is 0.8. Basically just use the trig functions to prove that, yep, same triangle. And since in the beginning, that's all they gave us was 4.5 and 6 and 3 and 4, is there one of these functions that just uses those two sides? I'll give you a hint, TOA. Tangent equals opposite over adjacent. So really, yeah, the 3, 4, 5 triangle is not that hard, but we had tangent equals opposite over adjacent. So opposite over adjacent for this one?
4 over 3.
4 over 3. Okay, 4 over 3. What, roughly 1.3333333333?
Yeah.
We'll call it 1.3. Because we're lazy. And what about the second triangle? Opposite over adjacent for this one? Because those were the numbers that they gave us, 4.5 and 6. So which one's opposite?
6.
So y over adjacent. What's the number?
1.33.
1.3333 or 1.3. Related. So we've just used trig identities to verify that these are the same triangle, and since that's the whole rationale for having a comprehensive list of every combination, is that it doesn't matter which of those sides they gave us. They could have given us y and r, could have found one that fits y and r, didn't have to use Pythagorean's theorem at all to prove that. So no matter what process we're trying to do to get it into a format that we can verify that it's the same, we can choose one of these that, as long as they've given us two, and one of these combinations is going to fit it. That's why we can pretty much spend most of our time just focusing on sine, cosine, tangent. And the others are good to know, but since if we had to know y and r to get sine, we have to know y and r to get cosecant too. So it's not that it gives us any additional tools, but it can be useful in some situations. I say some situations because it's really useful when you go on to like calculus and things like that, but since we're not, we'll kind of go, okay, that's nice. We'll see you later. And we'll focus on sine, cosine, tangent. Because when we were getting into all the stuff that that's useful for, it's just sine, cosine, and tangent, and your calculator probably doesn't have a cosecant button anyway. At least I highly doubt that it does.
No.
So the next step that we're going to be getting into is using the angles, because we use the functions to find the ratios, and that's good. We can also use the angles to find the ratios if we know the angle. So if they didn't give us any of these sides, but they gave us the angle, we know that how that ratio of those sides are going to relate to each other. So we know that if they've given us a 75-degree angle, we know that the ratio of this side to this side, even though we don't know the size of the triangle, we know that the ratio is going to be absolutely consistent. That's why when you type in sine of a number and hit equals, it's going to give you a number. It's going to give you a ratio of two different values. And so that's going to be the next step. And then after that is, what if we have the ratio and we want to find the angle that led to that ratio? We can use the calculator button to go both ways. So, talk too long again. So if you work on these, and yeah, this one on this set is 3 through 28. So problems 3 through 28. Section 4-2.
Sine inverse be cosecant?
What?
Sine inverse?
Nope. Sine inverse is.
No.
Don't
I'll
do
give
it.
it inverses.
Don't do it.
Inverse as the ratio cosecant is the inverse of the sine function. The notation that they've given on the calculator means sine of an angle is a ratio. Inverse sine of a ratio is an angle. So that sine to the -1
Yeah.
is actually plugging it into the ratio to find what angle led to it. So that means that we type it in from 0.8, so sine to the -1. Actually, stop checking.